Today we are moving to chapter 2 about joint distribution function, conditional probability and independence. The outline of this chapter are as follows. We will cover the joint distribution function, independence, conditional probability, conditional expectation and joint MGF. Okay. So today for this section we will cover the multivariate random variable and the joint distribution function. Okay. What is meant by MRV, multivariate random variable? So multivariate random variable can be denoted by X, which covering x1 until xn as an n-dimensional random vector whose components are random variables. Then all the definition given for bivariate random variable can be extended to the multivariate case. So there are two types of MRV, discrete and continuous. So in other words, if we apply the bivariate case, the same concept and theory can be applicable or extend to the multivariate random variable case. Multivariate means can be up to n. There are many random variable. So in chapter 1 we only cover single random variable, and for this chapter 2 we will cover for the bivariate or MRV case. Okay, so either bivariate is two random variable or the MRV, the same theorem are applicable. So first of all, we start with the discrete MRV and the joint PMF. The theorem says that if x1 and x2 are discrete random variable with joint probability function, then the joint PMF is written as follow. Okay, so these are the mistake of notation because this mentioned with x and y, but here since it is defined as x1 and x2 as a two random variable, then the joint PMF should be written in this way, in which the function of x1 and x2 is the joint PMF can be written in this form. Okay. And then this joint PMF should fulfill the two conditions in which the probability of the joint PMF should be positive, and then the sum of the probability should give us unity. So these two conditions is actually similar to the single random variable case. And this one show the relationship between the joint CDF and the joint PMF. Okay, so if we are looking to or would like to find the joint CDF, then we should use the sum up of the joint PMF to obtain the joint CDF. Next, we move to the continuous MRV case. Two random variables x1 and x2 are jointly continuous if the probability of any event involving both of them can be expressed as an integrate of a probability density function. So this is the joint PDF. Okay, so the joint PDF is defined to be the double integral of the joint PDF function. Okay, so I think this is again the wrong notation, should be dx1 dx2. Okay, this term should be a bivariate function can serve as a joint PDF of a pair of continuous random variable if its value satisfy the continuous condition as stated here. So in which it said that the probability value should be positive, and then again the double integral or the sum up of the probability will be unity. The joint PDF is linked to the joint CDF in the following way. Okay, so if we would like to find the joint PDF by given the join CDF, so we need to do the derivative. Okay, so if we would like to find the joint CDF, we have to do the integral of the joint PDF. So the same concept is found in the single random variable case that we covered in chapter 1. Okay, so this is the additional distribution function that cannot be found in the single random variable case. Now in the bivariate case, we have the marginal distribution. Okay, so joint CDF already understood as a joint of the cumulative distribution of the two random variable. Okay, so as defined as follow. Okay, and then this is for extra information, the theorem that stated the property of the joint CDF. So the joint CDF have the following property, in which the given, okay, so this is the bivariate case. If we have x1 and x2 as the random variable, this is the joint CDF. So we show the value of x1 and x2 approaching negative infinity, then it will give us approximately 0. If x1 and x2 approach the positive infinity, then it will approach 1 for the joint CDF. And if we define A smaller than B and C smaller than D, then the joint CDF taking the value of A, C will be smaller or equal to the joint CDF of the value taken B and D, the range. Okay. And then number 4, if we define A smaller than x1, B larger than x2, then we have this condition hold. Okay, so this condition is hold by referring to this region of the probability. Okay, so we have the condition here. We have A and B. Okay, it said that okay, A is smaller than x1 and B is larger than x2. Okay, if we want to find the joint CDF of the range taking the interval A and B, which is this distance. Okay, it said that this distance minus the distance of A and A2, and then minus the x1b, x1b. Okay, so this term minus this distance minus this distance plus the distance here, it will at least 0 or positive. Okay, so this is based on the probability value that it will be positive. And then next one, we have the marginal PDF. The marginal PDF of x and y is as defined here. So okay, so meaning that, so this is the continuous case. Okay, for discrete case, you will replace the integral with the sum term. Okay, summing up. Okay, so what is mean by marginal PDF of x, marginal PDF of y? Marginal PDF of x is defined as the function that x is fixed and y is going to change. Okay, will change from different value. And the marginal PDF of y say that y value is fixed, but x is changing the value over time. Okay, so for further explanation, we may refer to the example. Okay, so we may move on to the example here. So there are different examples which covering the distribution function, joint BMF, joint PDF, joint CDF, and marginal PDF. Okay, for example A, we have 3 socks in a box which take the number 1, 2, 3, and then we take out 2 socks at random without replacement. X is the number of the first sock selected, Y is the number of the second sock is taken, and we have the following result. Okay, so X represent the first sock, Y represent the second sock. So the possible outcome will be you only have one. The number show number 1, number 2, number 3 for both X and Y. And then following the theorem, it will be sum up to be 1. So this is the discrete case. So the discrete case is a joint BMF will sum up to be unity, as mentioned here. So then we would like to find the following joint BMF: x2, y2. Okay, so x2, y2 will give us 0, and then x2, y1, which is 1/6, and then x and y smaller than 2. Smaller than 2 means it is the possible outcome is 1. So x1 and then y also 1, which will give us 0. And if we want to find larger than 2, both x and y, so larger than or equal to 2 will be 2 and 3. Okay, so it will be a combination of 2, 2, 2, 3, 3, 2, 3, 3. So we just add up, then we will get the solution. And then for example B, we follow from the example A above, but now we would like to find the joint CDF. So the joint CDF of x smaller or equal to 2 as well as the y. So meaning that we would like to find the joint CDF of 2, 2. Okay, joint CDF is obtained by the sum up of the joint BMF. Okay, so which is you sum up all the possible combination, and then you find the combination, substitute here, you get the solution. Next one is the marginal distribution. Okay, so still apply to the same example. Now we would like to find the marginal distribution of x. So marginal distribution of x meaning that x is fixed at a number. Example, we want to fix x equal to 1, and the value of y are changing. Okay, so y is changing from 1 to 3. So the possible combination will be x1, y1, x1, y2, x1, y3. So you substitute the value here, you get the solution. And then next one is the marginal distribution of y, meaning that the value of y is fixed and x are changing the value. So y is fixed at 2 and x are varying from 1 to 2 to 3. Okay, so the combination will be x1, y2, x2, y2, x3, y2. So you get the solution. Example D. Okay, so example D is the continuous case. We would like to find the constant C here. So we are given a joint BDF and we do not know the value of C. So according to the theorem, the sum up of the joint PDF will give you a unity 1. Okay, so we have a double integral. Okay, the interval is defined 0 and 1 for both x and y, and then we equalize to 1 in order to solve to find c. Okay, then solving the integral equivariant to 1, we finally get the solution of c. Okay. Next one, example E. We are given again the joint PDF function, and now we would like to find the term, this one, the probability x plus y larger equal to 1, and we are given the interval in the set A. We define the value of x and y, which given x plus y larger equal to 1. Okay, so we know this, and we also know x and y are between 0 and 1. Combining this information and written in terms of x, okay, we can write in the following way. Okay, because x plus y, okay, larger equal 1, then to write in terms of x, we can write so this one will give us to be something like right, 1 minus x, but in terms of x will be 1 minus y. So that's why we so we are written in terms of x, so x will be varying between 1 minus y, like this, or 1, and then x 0 and 1. Okay, so from this definition on the value of x and y, we can proceed to solve this term. So this can be obtained using the double integral function, okay, of x and y, and then so the first term, we first have to solve the dx. Okay, so dx, okay, and the x is varying from 1 to 1 minus y, these two interval, and then dy, y take the value between 0 and 1 here. Okay, so then solving, we will get this as our answer. Okay, next one is example F. Example F is to find the continuous random variable with the marginal x and y. So again, we apply the formula, but this is a continuous random variable using integral. So we would like to find marginal x, meaning that x is fixed, but the value of y are changing between 0 and 1 in the interval. Okay, so the interval of y is changing, so dy, and then we solve and get this solution. Same goes to marginal of y, meaning that y is fixed but x are changing between 0 and 1, so it is dx.